Okay, so now we are going to use everything we've learned. We're going to draw these molecules' Lewis dot structures. We will need to predict their shape in order to determine whether they are polar or nonpolar. We can also do some other stuff. We can predict what the hybridization of the central atom is, whether their bonds are polar or nonpolar. So we've learned a lot so far. So let's go through these four. And again, at any time you want to pause and try some on your own, you should. I would suggest at least trying two on your own, and then checking, starting again and seeing how you did. So the first one is CO2, carbon dioxide. Carbon has 4 valence electrons. Oxygen has 6 times 2 because there's 2 oxygen. So that is a total of 16 valence electrons. Carbon is in the middle. We make a bond to each of the oxygen. I subtract 4. I'm left with 12 electrons. I can now put those electrons right on the outside atoms first. And what I'm going to do is use up all my electrons. And so in this case, this is the exact case that we need to use a double bond. So, right, this is called reassigning. So I remove 2 electrons from a lone pair and make them into a bond. And I'm going to need to do that on both of them. So this is the final Lewis dot structure for carbon dioxide. You can see that the central atom has 2 electron domains, so that means the hybridization on the carbon is sp. Each of those bonds themselves, a carbon-oxygen bond, is polar. But because the shape is linear, right? The main question that you ask yourself when you're trying to figure out if a molecule is polar or nonpolar are the electrons symmetrical? Right? And the electrons are symmetrical here. If you want to use the flow chart, right, look at that. Does the molecule contain lone pairs on the central atom? No, it doesn't. Are the outside atoms the same? Yes. So that means that it is non-polar. The next molecule, dihydrogen monosulfide. Each hydrogen has 1 electron, and there's 2 hydrogen, and sulfur has 6 for a total of 8. Sulfur is the central atom. I use 4 electrons, which means I have 4 left over. I don't need to put any more electrons on the hydrogen because hydrogen is stable with just 1 bond. So I put those 4 electrons on the central atom. Now this is where it gets tricky because as I have drawn it with this Lewis dot structure, it kind of looks like it might be nonpolar because actually looking at these two, they look somewhat similar. But that's why shape is so important, because the actual shape of this molecule, if you go back to that table, 4 electron domains, 2 lone pairs, is bent. A more accurate Lewis dot structure would be looking like this. When I draw the molecule like that, it makes it look obviously polar. Hybridization on the central atom, there's 4 electron domains around sulfur, so sp3. And if you go to the flow chart, remember, if there's lone pairs on the central atom, it's almost always polar, so it was real easy to use that flow chart. O3, this is a molecule called ozone, right? It's important in environmental science. So 3 times 6 or 18 valence electrons. Obviously oxygen in the middle and oxygen on the other side. So now I have 14 electrons left over. I put them on the outside atoms, that's 12, 14 on the central atom. So I've used up all my electrons and I do not have a full octet on every atom, so I'm not done. I need to do something else. And this is the exact case when resonance comes into effect. Because would I choose the molecule on the left to make the double bond with, or the oxygen on the left or the oxygen on the right? And the answer is that both of those are the same. So resonance is when you can have 2 identical Lewis dot structures. And remember, I like to draw these as the hybrid structure, which means with a line and a dashed line. Right? I can't really do much about putting the outside electrons on and have it look have it look like everything has a complete octet. So we just kind of leave it like that, because in order to do the shape, in order to do everything else, all I do is look at the central atom. So hybridization, how many electron domains off the central atom? So a lone pair counts as 1 and a resonance bond counts as 1. So this has 3 electron domains. So sp2, hybridized. What's the shape? 3 electron domains, 1 lone pair is again bent, right? And because it is bent, it becomes much more obvious that this is in fact a polar molecule. That's a great example of a polar molecule with nonpolar bonds. And CH2Cl2, carbon, 4 valence electrons. Each hydrogen has 2, and each chlorine has 7. So 14 plus 2 is 16, plus 4 is 20 electrons. Carbon in the middle, hydrogen, hydrogen, chlorine, chlorine. I just used 8, which gives me 12 left over. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Everything has a full octet, so I am done. Now, looking at this molecule, it has 4 electron domains. That means the shape is tetrahedral. And tetrahedral, no lone pairs on the central atom, so it could be polar or nonpolar. The question is, are all the outside atoms the same? And they're not. So this is a polar molecule. And you may be saying, like, but look at it, it's really symmetrical. The way that we have drawn it in 2 dimensions, it does look symmetrical, but in reality, this molecule is not in 2 dimensions, right? And if I were to draw this maybe a little bit more accurately, we could have a hydrogen here and a hydrogen here, all in the same plane of the board, and then coming out of the paper would be a chlorine, and then going into the back of the paper would be chlorine. And if you think of it like that, yes, one side of the molecule would be more negative than the other. Which side do you think would be partially negative, and which side do you think would be partially positive? Yeah, the hydrogen side would be the partially negative side, partially positive side, and the chlorine side would be the partially negative side, right? If I'm looking at this molecule up here, dihydrogen monoxide, the side with all of the electrons is the delta negative side. Okay, so you're going to try a bunch of these for your homework, and we'll look at them in class tomorrow, but bring your questions if you have any about how to tell whether a molecule is polar or nonpolar.